Welcome back, everyone. First, a few quick announcements. I posted something on Canvas. We've updated some details on the TA hours. We've assigned special offices to hold the hours in. It's basically in the hallway off the front office, if you know where the special TA offices are. And so look at these times. If these times aren't going to work for you, please let us know now. So there was also a problem uploading the video from the first lecture. I think the issue was we uploaded a test video instead, so the video from the first lecture isn't up yet. Again, it'll be linked off of here. I'll add the link once it's up there, and there'll be a playlist and so forth. Bear with us. We have some new equipment that we're still testing to see if it gets works. This is the first in-class trial, perhaps. But hopefully we'll get the kinks out by Monday. And then if you haven't seen the first homework is posted. It's due. It's going to be due a week from today. Okay. So it should be after the lecture today. You should have what you need to do it. I mean, it shouldn't be too hard. I just want you to get used to dealing with these randomized concepts in data. But if you have questions, ask me or come to the office hours. Post stuff on Canvas. One more thing. So some of the TAs are traveling and so aren't in town yet. This mainly affects the office hour. This Friday is not going to happen yet. So it's supposed to be office hours Friday from 10 to 12. Those won't happen this week. If things are looking grim on the first assignment, there's not enough time, kind of let me know, but try and let me know ahead of time, and I'll make accommodations if I put it too tight at the start of the semester. Any general questions about the organizational stuff so far? So great. So we're going to start today talking about some basic, high-level kind of statistical principles, and talk about how to think of these through hashing. And these will kind of be core concepts that I kind of want you to get used to thinking about, and these kind of ideas will show up later on in the semester many times over. This will kind of be a simple tour through kind of some of these, through some of these initial ideas. And so, okay, so the first most important thing that we want to cover is these, so IID, so data. So who's heard of the abbreviation IID before? Okay, and how many heard of it from 3190? And how many from machine learning? From elsewhere? Just reading? Okay. Okay, so a mix, and a lot of you haven't heard of it. So when I started grad school, I'd seen it written in papers, but no one ever explained it to me. So, and you can't type IID into Google, or at least you couldn't back then, and it didn't tell you what it meant. So it means, or usually other way around, it means independent and identically so distributed. So IID. Okay, and so what this concept is that there's something over here that's the real world, and there's some underlying distribution there's something that's going on. And in order to do data analysis, what we do is we continually draw these samples from this real world concept we're trying to study. Right? Okay, these could be customers who are visiting my store, users to the website, students in the university. They could be kind of the measurements of like a bird I'm observing in the wild, and kind of the kind of assumption that we're making is that each of these draws that we're getting is some data point here. X1, X2, X3, and each of these are going to be IID, which means that they're drawing independently of each other. What I observe for X1 has no effect on X2 or on X3. Okay, so there's no kind of dependence between them, and that these are all kind of identical to each other. Every time I make an observation, okay, every time I make an observation, I'm making the same kind of sort of observation. I'm doing the same thing over and over and over again. Okay? And so what's eventually happening here is that I'm going to get some set X. This is now an uppercase X, which is X1, X2, up to, say, some Xn. And so this is usually what I think about as the input data. So I've made some observations, this is my input data, and now I'm going to do analysis on this data and try to learn something about the real world that's going on here. Okay? And this assumption that they're all identical, they're all independent of each other, it's true in almost all the things that we'll study in this class. And it's not always true in practice, okay? But in order for the analysis to kind of be mathematically sound, it's super helpful to make, in order to make this assumption. Okay, so what we're doing is we're trying to understand this, and we keep making observations over and over again, and from the collection of all of these observations, we can draw some sort of pattern, draw some inference, understand the structure. If these are dependent on each other, it becomes more complicated. If every time we observe something, we're observing some different part, well, that's also more complicated. We have to kind of know how we're observing these different parts. Okay, and so sometimes you are observing this part and that part of something, and we kind of know that ahead of time, but we make one observation of this part, one set of observations here, one set of observations here, and then we apply the IID analysis in each of those parts. But this really permeates kind of is the basis of a lot of analysis that's going on. Okay, so hopefully this kind of makes sense. We'll kind of what I want to do is to kind of observe what happens when you have IID data in a very simple but general setting in this lecture. And then throughout the rest of the semester, we'll see it in much more complex examples. Okay. So in this lecture, so in this lecture, we're going to assume we're going to have IID set X, X1, X2, and so forth. And then we're going to say that each Xi, each object that we pick, is going to come from some specialized domain, and I'm going to use N here. Maybe I'll say this is XM. Okay, so it is going to come from this domain. I'm going to write it like a bracket on either side, and this is equal to the idea. I can use this to represent the set 1, 2, 3 up to N. Okay, so it's all the integers from 1 to N. This is just a shorthand notation for writing that. This symbol, if you haven't seen it, this means in. That means Xi is an element of this set I'm talking about. Okay. So this kind of abstract notation where every object I'm drawing is one of these is a number between 1 and N. Well, this is convenient to write stuff about. It's basically like you're indexing into an array, except usually in CS you start with 0 instead of 1. But you know, just that's a small detail. You can shift it to mean that if you want to. It's meant to be kind of an abstract setting, so that this can it can represent a lot of things. The set N can be, for instance, it can be all possible like IP addresses, right? So there's this huge number of IP addresses. What is it? Is it like 12 to the power 10? I think different IP addresses. So that's a huge number down. If that number is N, I might as well just talk about this set. It's going to be the same thing, right? It could be all words in a dictionary, or maybe I don't even need it to be a dictionary. It could be any possible scribbling of text separated by a white space inside, like Twitter, right? So it could be any possible word, right? It could be one of these elements, right? I may not even totally know the value of N here, but I just assume it's going to be something large in this case, right? As I keep reading stuff that people type into Twitter, I might observe a new string of characters every day, right? There are just a lot of possible strings of characters, right? And we'll see an example. It could be all, say, all possible birthdays. In this case, say N would be equal to 365, maybe 366 if someone's born on February 29th, right? But there are that many days in the year. There are that many distinct kind of days, which is your birthday. Okay, so then it's the n different values. So this is kind of just like a placeholder that allows us to talk about a bunch of different things. And in this setting, we're saying it's a set. It's just any set of size n, because it's a set. The relation between something being an object in spot 2 or object 3, it doesn't mean that they're necessarily similar to each other. Okay, so I'm not assuming that 2 is close to 3 in this case, where if these were actually meant to be kind of the amount of time I spent browsing on my screen time this week versus last week, if those two numbers are close to each other, that means something, right? In this case, it's just some sort of ID, maybe like a social security number, which in principle are kind of like, don't have that much meaning, although you can actually kind of make a pretty good guess of someone's age and where they were born based on their social security number, as it turns out. But it's not supposed to hold that purpose. All right? Okay. Yeah, so there is some relationships between birthdays in this way, and I'm saying I'm going to be ignoring that aspect. Right? So this is, again, this is one of the first like modeling choices. With birthdays, we can just say, okay, it's just one day out of the year, and that's what makes it distinct. But you could say they're like January 7th or January 8th, those are similar to each other, right? Or maybe if you were born here or you're born in China, those might actually be the same thing, depending on what your birthday is. So there's something I'm ignoring here, and I'm doing that for the simplicity of kind of analyzing what's going on. Right? Same thing with IP addresses or words in the dictionary, actually. Kind of misspelling of words are really close together alphabetically. IP addresses, which are similar, are probably from the same kind of, like the same subdomain. And this information is used in more advanced analysis, but initially we're just going to say these are just different things which are distinct. So, okay, so now I'm going to use this as the domain of the data points I'm drawing. I'm assuming they're IID. And I'm also going to add another assumption. Also assume that it's each xi is uniform in this in this domain. So that means that the probability that xi is equal to the value j is equal to 1 over n. That's if j is in n, and it's going to be 0. It's going to be 0 otherwise. Right. So for now, today, we're going to restrict to this simple case that it's just going to be uniform. Okay, and I'm going to and we're just going to kind of see what happens if this is uniform. Okay, and then later on in the semester we'll see that well, in practice for a lot of these things it's not uniform. For birthdays it's pretty close to uniform. But for IP addresses and words in dictionary, it's very far from uniform, and so we'll want to do other things to think about these sort of understanding the properties of this sort of data. All right, so you've probably seen something like this before if you've taken, I guess this is probably in like the data structures class in 2420. You've probably seen a hash table, right? So who's seen a hash table and who's not seen a hash table before? Oh, okay. So we'll quickly review what a hash table is. It's a very useful it's a very useful data structure for storing a set. When you, for instance, may not know how big the set is, you want to check if elements are in there. And what is critical for the hash table is actually the hash is the hash function. Okay, and so we're going to be, and I'm going to call this like so it's like a random hash function. We're going to talk in a few weeks about what's called a locality-sensitive hash function. So when I say a random hash function or a separating hash function, I'm referring to this object, which is probably what you've is probably what you've seen before. So a hash function is actually defined as a family with respect to a family of hash functions. Okay, and we'll call this a script uppercase H. Okay, and so then one hash function in here is so we'll say HA is here, and so this choice of which function I'm going to pick, which is this lowercase HA, this choice is random, but then HA is actually a function, so it's going to be deterministic. So this will be a function from some string usually to our domain n. Okay, so this is going to be deterministic. Okay, so I'm using this. I'll write down a string of length k because, or it could be maybe it doesn't matter so much what the length is, just because it's the right notation. But don't worry too much about it. It's some sort of input that is describing some object, some identifier, some word, some number, and it's somehow mapping it to one of the elements in the same domain I was talking about, this array of length n. Okay? And this function is deterministic, but I picked a random function from this family. Okay? And so the idea is that if conditioned on this random choice, I should be that the probability of two things colliding should be should be 1 over n. So idealistically, what I would like to happen is the probability over the choice. Okay, so the probability is over this choice of the random hash function that h of a of, say, string 1 is equal to h of a of string 2 is equal to 1 over n as long as string 1 is not equal to string 2. String 2. Okay, good. So as long as they're not equal, the probability that they hash to the same spot should be 1 over n. This is not for any hash function. For any hash function it's deterministic. It's over the choice of the hash function. Okay, so we're assuming somehow that we've randomly chosen a hash function, and then we have this mapping which is fixed. Okay, so if you've seen hash tables before, you've probably seen all this before. And so if you have the hash table data structure, just allows you to kind of store, for instance, the simplest version is you can store a bit and at any cell between 1 over n, and if you see a 1 bit there, then you guess that this object exists. You can also store the full object there, and there's more complicated variants of this. But this is the basis of it. All right, so it turns out we're going to need hash functions in this class, and you know, if you look online at how to choose a good hash function, there's not necessarily a lot of good. There's a lot of resources out there in like searches on Google which aren't actually correct. Okay, so let me give you a few quick recipes about how to choose a good hash function. Okay, so or a family of hash functions or something like this. So so the first class will be built-in built-in hash functions, and so these are usually pretty good. Like the ones in Python work fine. There are these hash maps and so forth, and they can take in a lot of sort of. You can put whatever object you want as the string, and it will hash it into bins as you want. There have been past problems with the Java implementation. I think I'm not totally sure if those are if those are fixed or not. If you're not totally sure if it's fixed, one example is the SHA-1. So this SHA-1 hash is essentially supposed to be a function that was supposed to be used for supposed to be used for certain security purposes. where if you know what the result of the function, you can't back engineer the function. And it turns out, and it's built into most languages, and it turns out it works as a pretty good hash function. Okay, it's a deterministic function, so we need to choose kind of a random element of it. And so one way of doing that is we can say HA as some input X is going to be something like SHA-1 of the concatenation of A and X. Okay, and so this A is what's called the salt, and the A is going to be is going to be some other string. So some string, and so in principle you should pick A at random as a string, say of length 5 or 10, you know, or even 3 should probably be fine, because it shouldn't. If two things are very similar to each other, they should map to kind of arbitrary points in this range so in between 1 and n. And so if you put any string in it, every time you pick a different string, the SHA-1 function acts in a way that's kind of, so it's basically unpredictable. Okay, it's deterministic and it spreads stuff out, but it's unpredictable. So if I change the salt, I'm basically creating an entirely new hash function. So I can create a random hash function by choosing some random salt, or essentially an arbitrary different string works just as well as random in practice. Okay, so if you don't trust what you have, this should be built in and should be pretty trustworthy. Other built-in hash functions, say in Python, also should work. If you need to make multiple hash functions, which we will, you need to add a salt each time so you don't use the same hash function over and over again. Okay, so adding the salt is going to be important here. All right, so the second class, so SHA-1 is kind of this mysterious thing that at some point was kind of hidden what it was. It's now known and decoded and so forth. But if you want to kind of do something from first principles, there's something called multiplicative hashing. Okay, so if you want to completely build your own hash function, you know, for optimization, you're probably better off using a built-in one because these are super efficient. But a simple one you can build yourself is going to be, this is the size of my domain. Okay, so this is n times the fractional part of x times a. Okay, so when I take this frac operation, so for example here, what's going on is say frac of 11.278 is going to return 0.278. It's going to return the fractional part here. Okay, and so again, this is going to be my salt, and I basically want to make this a large int with its. If I look at its representation in binary, it should have a good mix of zeros and ones. Okay, so if you pick up probably a large integer at random, it should probably work pretty well. Okay, if it's like exactly a power of 2, it might have some weird issues, or close to a power of 2. Yeah.
Does the salt change every time you use it, or is it
so it depends how you're using it. If you're building a hash table, you fix a salt, and each hash table has its own salt, and then it's fixed. But we will be seeing things over the course of the class where you need multiple hash tables, which you kind of stack together. And then you're going to need to change the salt every time, and you're going to get a different hash function. So you have HA1, HA2, HA3, and so forth. Right. So if you just use it as a data structure once, which is the typical thing then that you may have seen earlier, then you don't need so much to worry about the salt, right? But in here, it's going to be important. All right. And then, so both of these are good, safe options, or anything kind of built in as long as you're adding some sort of salt. So the third thing I would like to mention is what's called modular hashing, and this is basically h of x equals x mod n, right? So I think of it, I turn whatever my object is into some sort of integer, and then I do a mod n operation, right? So I take it keeps wrapping around and always maps to an integer. This is surprisingly recommended a lot, and at some point this was built into Java as one of their defaults, I think. So you should do not use this. Okay. So this is often, maybe not as often as it used to be, but this has been recommended in places that appears easy to say, oh, this looks simple, let me use this. This does not work so well. For instance, if you have two values which are off by 1, they will never hash together. They'll never hash to the same spot. Right? 17, 18 will never hash to the same spot. Sometimes you want them to occasionally hash to the same spot in ways which might not be intuitive now, but might be later. So that will break. And other things that are off by exactly m, they're always going to hash to the same spot. And that's also a problem. Okay, so there are some issues with this, and there's speed-ups of the multiplicative hashing where you can replace, oh yeah, this is the floor operation outside of here, these things. So that's doing the opposite of this. The floor of 11.278 is going to be 11. It rounds down. Okay, so there's ways to kind of speed this up if you're trying to worry about the kind of like very efficient machine code that replaces some of these with some mod operations. And if you don't do it correctly, you end up getting the same fallacies as the modular hashing. Okay, so be careful about that. There's a way to do this, which is h of a of x is equal to, I think, xa over 2 to some power q mod m, where you divide by some power, some 2 to some power q, and if you don't do this, where this is some large power, it's kind of this. It has the same issue. So you can show that if you do this some large enough power, stuff kind of works out, and you can store this and turn it into a multiplication and make it faster. If you're really worried about speed, use one of the built-in functions, or download some really fast library meant for this sort of thing. I wouldn't try and implement yourself unless you just want to play with it. Okay. So hashing, and okay, so we have these hash functions now, which will essentially, I'm not going to go through exactly why they work so well, but they will essentially act like this distribution we want to talk about here. We're going to draw a bunch of these xi's from some distribution. Each of them is going to have value between 1 and n, or maybe 0 and n minus 1. Don't worry about that distinction. And the probability that they're going to collide, being the probability they're both going to wind up at some value j, is, if the first one winds up at some value j that the second one will as well, is going to be roughly 1 over n. Okay, so it's basically going to act like this uniform distribution. Okay, so we have these hash functions. This is a thing that actually exists. So let's kind of look and see some properties of this. All right. So we have let's think now. Our input is going to be a sequence of distinct strings, each we hash with HA in some hash family, HA of our string into the domain N. Okay? So now the first question I'd like to ask is how many until a collision? Okay? So this is an abstract, kind of a more abstract problem. A concrete version of this is what's called the so the birthday paradox. So who's heard of the birthday paradox before? Okay, so in prob stats, I guess you also do this. So the birthday paradox says that if you have roughly about 23 people in a room, that the probability that some pair of them will have the same birthday is going to be about 50%, is over 50%. Okay, this seems strange. There's 365 different birthdays, but when you have about 23 people, the probability that some are going to have the same birthday is about 23, is over 50% already. Right? So this seems kind of odd, but that's saying if n is equals 365, then after I've seen about 23 different strings, I'm probably going to have a collision. Right? So this means that your hash table, your data structure, needs to deal with collisions because this 23 is much less than 365, right? So I want to kind of explain, go through just a little bit what's going on here. Have you guys simulated the birthday paradox in a class before? Okay, so we could do that again, or you've seen it before? No?
Oh, let's review it.
What?
Let's review it.
Sure, okay. So we'll do this quickly. So how this will work, you don't need to review your actual birthday, but pick a date now in your head and fix it. Okay? And what we're going to do is we're going to go through the class and you call out a date, and then we'll see how many it takes until it collides. And as you know, it should take about 23 people, and that's the expected number. Or the probability when I reach over, the probability when I reach over 50%. The number when I reach over 50% probability is 23. Okay, so the fastest way to do this is to write out the months. Did I miss any months? Okay, good. Okay, so we'll go through the middle part of class and just, you can tell me a date.
January 1.
Jan 1, okay.
August 25.
June 25th.
December 3rd.
February 8th.
August 20th.
April 24th.
That's someone coming up soon. What?
November 3rd.
November 3rd?
November 13th.
Actually, today is my birthday, January 9th.
Oh, so happy birthday.
Thank you.
December 27th.
February 15th. May 17th.
September 17th. Me?
Yeah.
April 19th.
February 27th.
June 8th.
May 17th.
May 17th. All right. So how many was this? So this was 18. All right, so this was 18 trials. I said 23 was the point where we reached over 50%. I think it's about 53% for 23. I think I've got the number written down for 18. I think that's about, what was that? Yeah, so 18, there's about a 34% probability that we would hit it by the 18th person, actually. Okay, so this isn't unreasonable. So about a third of the time we would run this trial, within 18 people we'd actually have a collision, which seems, I don't know, this is slightly unintuitive. So let's just spend, I mean, maybe you've analyzed this before, but let's just kind of spend a few minutes just analyzing what's going on here. All right, so the probability that the first person collides with someone previous to them is 0, right? So the first person has 0 probability of colliding, but the second person has a probability of 1 over n of colliding, right? So the probability that S1 equals S2 is equal to is going to be equal to 1 over n. Okay, and so if we have, so that means that any pair of people that I'm testing, if I just look at that pair, the probability of them having the same birthday is going to be 1 over n. Okay, so if I have k, if I look at ask k different people, so with k people, that means I'm going to have k choose 2, which is, I can write this exactly, is equal to k minus 1 over 2 pairs. All right? So they're roughly k squared pairs after I've asked k people. So if I write down the probability of any one of them colliding, well, it's easier to say. So the probability of no collision on k pairs is going to be equal to 1 minus 1 over n, right, to k choose 2. Right, so if I just look at k pairs, the probability of colliding, of not having a collision, is 1 minus 1 over n to the power so k choose 2. So if you take this and you plug in n equals 365, and you plug in k equals to 23, then you get the probability of no collision is going to be, so for n equals 365, k equals 23, then this equals 0.467. So the probability of not having a collision, not having a same birthday, is about 47%. That means with 53%, some pair probably had the same birthday. Okay? So this is roughly what's going on, but this actually is not correct. Okay, this is not the complete analysis of what's going on here. All right, so what's wrong with this?
It assumes that there's equal probability for each day to have a birthday on it.
Sure. Sure. So, okay, good. So the first point is this: assume a uniform probabilities of some birthdays. And so this is pretty close to being true. If you look up statistics, there's I think slightly more birthdays in the fall. I think September is the peak, but it's pretty even. Okay. The other issues, there's actually, say, 366 days. Someone could have a birthday on February 29th, which occurs once every 4 years, roughly. That's also distorts things a small amount. There's also in like a classroom setting in a room, there's probably a non-zero probability of having twins who probably have the same birthday as well. Right? So there's various things where this is not the same, but it's pretty close. And so from a modeling perspective, this is, like, I would say it's a reasonably good model of birthdays. It probably changes less than changing from k from k to k plus 1. It's less than that probably is this modeling error. So this is probably not that large of an issue. Does anyone see okay, is there another issue with this analysis? This is a good point. It's good to think about these sort of issues, and sometimes they will be more severe. But this case it was okay. All right, so what happens? So I want to know the probability of no collision after I've talked to k people, and let's say k is equal to, what happens for k equals to 366? Okay, if I plug this in, I'm going to get the probability of having no collisions be 1 over n to 366, roughly, choose 2. Some very large number.
That number's going to approach 1, but never quite be 1, although we know it's guaranteed that there will be a collision after n is...
Yeah, right. After I've asked 365 or 366 people, I must have a collision. So, so this phenomena is called the pigeonhole principle. It's a very old principle, I guess, when people kept pigeons, and they had more pigeons than they had holes where pigeons went into, and so some hole must have more than one pigeon in it. That's, I believe, where it comes from. But it's got a great name now because of that. So once I've reached 365 or 366, I must have a collision because I will have covered every single birthday. Okay, but this analysis says that this is going to be, this is very small, but it's strictly greater than 0. Okay, so something is wrong in my analysis here. Okay. So what's actually going on is that the probability, so the true probability after k steps should actually look like 1 minus n minus 1 over n minus 2 over n, right? So this is this number is the probability that the second person collided with the first. This is the probability that the third person collided with either of the first two. Right? So when I see the third person, I know that the first two didn't collide. So that means that the third person has a higher probability of colliding than the second person did. And it doesn't make much difference now, but n minus 3 over n up to n minus k over n. Right? And when k gets big, right, then this probability goes down. And when k equals to n, then this probability is 0. 1 minus 0, the probability of a collision will be 1. Okay, so this is equal to 1 minus it's the product of I equals 1 up to k of n minus I over n. Okay, and if you haven't seen the symbol, it looks a lot like an uppercase pi. It's like a sum, but it's for multiplication, right? So it's the product. So who's never seen that symbol before? Okay, good. So, Okay, and if you type in LaTeX, it's /prod, it's not /pi, those are different symbols. Okay. Okay, so this is the right analysis of what's going on. Okay, but this other analysis was a pretty good guide of what's going on, and it basically said that we have a probability of collision is going to be, say, greater than 50% after about square root 2k steps. Okay, so so after k equals square root 2n steps. Okay, so if I do square root of 730 is going to give me about, so I think it's 27 is roughly 2 times 365 square root of that. So it's this back of the hand kind of guidance gave me about 27 for the number when it was 23 was closer to the right number. But it basically means after about square root n steps, roughly, I may expect to see a collision. Okay, and maybe you're telling algorithms that this is still polynomial, but when n is big, this is much, much, much smaller than n. 23 or 27 is much smaller than 365. Right, and this phenomenon gets worse as n gets bigger, kind of in the fraction of n that it takes. So my hash table of a lot of empty cells when I first get my collision. Okay, and this does not concentrate that well. So if I look at this probability, if I want instead of greater than 50%, I want to change that to say 33 to 2/3. So I want to capture roughly, so k equals to 18 as what we'd observed in class. The probability of the collision was about 34, and k equals to 28. I think is the probability of collision was about 64. So there's a range of 10 around the 50% mark that contains 30% of the probability. This is a fairly large spread. This is spread out fairly well. I've run this in class where it took, I think, close to 50 steps before we found a pair with the same birthday. And I think, and when k equals 50, you get to about 96. The probability is about 96% of the time. So this was pretty rare. It took me about 20 classes for this to happen. But 1 out of 20 is not that rare, right? So I might get to 50 if you'd only budgeted for 23, you might get twice that many, and that should not be out of the ordinary. So there are other things we'll see which are more concentrated than this, where it really happens right about when you'd expect it to. All right. So let's with the next question, let's keep asking, what happens if we keep going through more and more people in the class? Kind of the next, I think, big interesting thing, question 2, when do we see all birthdays? Right, so how many steps do we need until we see all of the birthdays? Okay, as we discussed with the pigeonhole principle, this must be greater than n, right, or greater or equal than n. But it's probably not going to occur just then, right? As we saw, we're going to have some collisions most likely, so it's not going to happen right when we get to n. But how much bigger than n do you think this is going to be? If the first collision is about square root n, about how long until we see all of the birthdays? Any suggestions?
Squared?
What? Squared. So one suggestion. Yeah. And squared? Anyone else have a guess? No, everyone thinks it's n squared?
2/3.
What?
2/3.
N to the 2/3.
No.
N to the 2/3 is, well, that's kind of like you could,
1.5.
so 1.5. Okay, good. N to the 1.5. So n to the 1.5 would be 365 times 20 times 20, right? So okay, do we want to vote on these two options, or someone want to have a third option?
Are we asking when the probability is over 50 that we've seen all
Yeah, or
birthdays?
the expected values,
And
something like that. At n. Okay, and then n. Right, so roughly n, maybe like, I mean, not exactly n, maybe twice n or something.
In that magnitude.
Okay, so let's, yeah, so like, it's like theta.
That's exactly
Theta
right.
event. All right, good.
N log n?
And log n. So, okay. Anyone else have a guess? All right, so let's. Oh, yep.
Factorial.
N fact. Do I write factorial question mark? Is that? Yeah. So or this is n factorial. Yeah. Okay. That's a pretty big number. Okay. So let's. I think we've had enough suggestions. So let's have a vote. Who thinks? Just raise your hand. Who thinks n squared? Okay. About 10 people. End of the. Let me write down my votes. 10 people. End of the 1.5. Okay. About 5 people. Okay. Theta of n. Okay. So this is about 25 people. Okay. So n log n. Okay, it's about 40 people. And so let's see, by process of elimination, there's should be about at least 50 people left in the classroom. So I'll mark it. So 50 people for n factorial? No? Okay, then a lot of you didn't vote. All right, so it turns out the right answer is actually n log n. So this problem also has a cute name. This is known as this is known as the coupon collector's problem. So say you're at McDonald's and you get a Happy Meal and you're given a random toy and you're supposed to collect all the toys. How many Happy Meals do you have to buy until your kid gets all of the toys, or maybe for you? So it's about n log n of them. Yeah.
Is that derived from the negative binomial distribution?
There might be a relation to that. We'll go through a derivation that doesn't need to use anything about that. Yeah. So this is like I'll also study a lot, and you know, this will. Yeah, you can imagine cases where you want to see some event, and there are a bunch of different events, and you want to make sure that you see all of them. You have an example of every kind of type of, you know, if there are different types of students in the room, and I want to get one example of each, I may need to do an extra log n factor to get all. Log n isn't too big. N to the 1.5 would be actually a large markup. That's a factor 20 just for birthdays, right? It's actually only a log n factor, and that's was log of 3. And it's log base e, turns out. So it's natural log of 365. That's probably, it's maybe like 7, something like that. At that scale, but when n gets bigger, this is a much more significant difference between these. Okay, and it's not theta of n, it's actually this extra log n factor. So the right way to analyze this is you want to so you want to analyze a sequence, and you want to say, you have a sequence of, say, S1, S2, S3, S4, up to SK, and you want to mark in the sequence if this is a new observation. Right, so the first one is always new. I haven't gotten that coupon before. The second one is probably new. Maybe the third one I resaw the coupon I saw in the second step, so it's not new. Okay, and then the fourth one is new again, and so the way to think about this is say let Ti be the number of steps until the ith distinct observation, and then we'll say lowercase ti is going to be ti minus 1. So this is equal to number of steps between the I minus 1's distinct and the ith so distinct. All right? So this ti, what we want to understand is this is the, let's say, the expected number, expected value of ti. Okay, and so the expected total number of steps, the expected total number is going to be equal to the sum over I equals 1 to n of these ti. Right, so if I understand what this value ti is, I just sum all these values up. Okay, this makes sense so far. So if I understand at least the expected, so that's expected value, but by the linearity of expectations, I can write it like this. So I just need to understand the expected value of one of these ti's. Okay? Okay, so what is the expected value of ti? Okay, so this is saying I've seen I've seen I minus 1 of the coupons, and so I need to say the number of expected steps until I see one of these ones that's new. So let's first say that the probability of seeing ith distinct given I minus 1 distinct ones I've already seen, right? So I've already seen I minus 1 different ones, and I want to see the ith one on the next step. So the probability of seeing that on the next step is going to be 1 over n minus I minus 1. Okay? And so then now the expected number of steps until I, oh yeah, so this is the binomial distribution. Okay, so the probability that the expected number of steps until I get this is 1 over this probability. Right, so now that means the expected number of steps I need to take, where each one is at this probability, they're all going to be independent, right, is going to be 1 over this, and this is n minus I minus 1 over n. Oh, no, I did this wrong. Okay, so this is, okay, let's leave it up here so you can see that I can make mistakes instead of just erasing it, but that's not the right probability. Okay, the right probability, as I have in my notes, I should have looked at, is n I minus 1, which is over n, which is n minus I plus 1 over n, right? So this is the number of open positions that I haven't seen, right? And that's just pushing the minus through, right? Okay, so then the expected number is 1 over that, which is n over n minus I plus 1, okay? Okay, so I know the exact expected number of steps to see the ith distinct mu1 once I've seen I minus 1 of them. And so now that looks like it might not help too much, but if I write down the sum equals I equals 1 to n of ti, or the expected value of ti, this is sum I equals 1 to n of n over n minus I plus 1. Okay? Well, I can factor out the n. And I have this term n minus I plus 1. What do these values look like? Well, let's, if you're not sure what to do here, start with I equals 1 and just write these terms out. So if I is equal to 1 here, then I do n minus 1 plus 1. So the first term is 1 over n. The next term is I minus 2 plus 1. So I've got 1 over n minus 1, 1 over n minus 2, up to, so 1. When I plug in n, let's actually, 1 over n minus 1. When I plug in n in there, I'm going to get n minus n plus, actually that's 1. Okay. Right, it's 1. Okay? That means there's actually a simpler way to write this. I can change the meaning of the index here and write this as n I equals 1 to n of 1 over I. Okay, now this looks a little simpler. And so this term here is known as Hn, which is the nth so harmonic number. Okay, and so this is, this is a known, it's a known quantity. H of n is going to be equal to some constant plus natural log of n plus a little o of 1. So there's, depending on n, there's some term which is less than 1 and it stays asymptotically smaller than 1. Okay, or it's less than 1 over n. It's pretty small. So I can basically ignore this term. This is log n, and this constant is known to be about 0.577. Okay? So then the overall sum is then going to be the overall total number of steps is n times h of n, which is basically n times 0.577 plus the natural log of n. Okay, so it's basically n log n. But I actually have a pretty tight estimate of the expected number. And this turns out to be much more well concentrated. So it's really ends up being pretty close to this relative to 0. Okay, so this is the coupon collectors phenomenon. When I finally see all of the coupons, finally all the pigeonholes are filled. So it's going to be roughly n log n at this stage. Okay, so I want to briefly say that this is, oh, yeah, question.
So I have a question on so the probability of seeing the distinct is this. So for the expectation is descriptive, like shouldn't it be like 1 into I? For the expectation of Ti, you have to get the probability of each I multiplied by its value, right?
So this is kind of you can look at the expected value of the binomial distribution. There's one way to see this, or you can kind of intuitively think about it. Just a minute. So every time I flip a coin, let's say with probability 1/10, it's a heads. Otherwise, it's a tail. It's an extremely unfair coin. Okay. How many times do you expect to have to flip it before you see a heads? Right, it turns out the expected value is every time I have a 1/10 probability, and so when I add up 10 of those trials, it's going to expected value is 1. So that's expected total number. That's not. But the expected number of trials turns out also to be 1 over that number. So this is kind of a tour of kind of this sort of phenomena that show up, and we'll see kind of variants of these showing up within the analysis of different algorithms, right? We'll say we want to hit, there are K clusters, we want to hit all K clusters. How many kind of random darts do we have to throw at the board to make sure we hit them? That's essentially a strategy that we'll use later on in the class. Right, and the coupon collector kind of tells us we need about K log K darts if they're all equal probability. All right, so I give different notions. This is talking about expected value with the birthday paradox. I talked about the probability of collision becomes over 50. I had these different notions, and that's because those are the cleanest analysis of what's going on. What's typically done is a model of writing these sort of randomized processes. I mean, there are different things in statistics, but in data mining and in general in kind of computer science analysis, what people use is what's called probably so approximately so correct. Okay, so it's not just probably correct, it's not just approximately correct, it's probably approximate correct. It's an approximation algorithm and a probabilistic algorithm together. Okay, and this is typically what will happen. We're not going to ever be able to get the exact solution often, or we don't care to, and we may need to use randomness or assume the data has randomness, so everything is going to be probabilistic. And so the right way these bounds are, and this is known as a pack way of thinking, probably approximately correct, is to say that we want to estimate some quantity mu, and this is the simplest version of this is when we're trying to estimate the mean of something or the expected value, and we estimate some value x hat. Typically, if I put a hat on some variable, that means it's some estimate. It's some estimate from data is usually what the hat tells me. And so the probably approximate correct ends up writing something that looks something like this. where you say the distance between x hat and mu, so the probability that that distance, or the difference between them, is greater than some epsilon is less than some delta. Okay? So this is an error term. This is my, my acceptable error. So the acceptable error tolerance I'm willing to say. So the probability I exceed my acceptable error, I want that to be my probability of the probability of failure. Okay? So this is, delta is the probability I've exceeded my acceptable error. Okay? And if there's a high probability I'm close, so it's similarly, instead, I can write this as the probability that x hat minus mu, this difference, is less than epsilon, is greater than equal 1 minus delta. All right, in this case, both epsilon and delta are going to be some, so delta is a probability, so delta is going to be between 0 and 1. Okay, and epsilon, you know, it's easy to think about if x hat and mu are in some range between 0 and 1, let's say they're also a probability or something like that, then you would also want epsilon to be much less than 1, right, and 0 to be less than epsilon. Right, so say I'm trying to estimate a probability, then I may want within 1%. Right, so the probability I'm off by more than 1% of the, say, would be less than, say, 5%. So, so something kind of like that. And in this setting, when I'm in here, typically, then this says then the number of trials is going to be roughly 1 over epsilon squared log 1 over delta. Okay, so kind of if I'm able to kind of assume something that x and mu and each of my random observations are kind of bounded between 0 and 1, otherwise I can scale stuff. I can scale the epsilon term in here as well. But if they're between 0 and 1, this is a simple setting, then I roughly need 1 over epsilon squared times log 1 over delta. So a lot of these things, what this basically means is that I can, so hopefully you'll have taken a stats class or the 3190 and you've seen something like I'm trying to estimate mu, and I've got some distribution of where this is the PDF of x hat, okay? And so that there's some acceptable tolerance, that's epsilon, and that I've got some tail probability of failure, which is delta. Okay, and as I get more and more trials, this is going to become narrower and as it's going to fit around here. And so if I fix epsilon, very quickly the tails are going to shrink because it's the number of trials, this is inside of a log. If I fix delta and I want to fix the tails and I want to the size of the tails and shrink epsilon, this requires a lot more trials, right? If I want 1%, 1 over 1% squared is going to be 10,000. Okay, if I want 1% probability of failure, I log 1 over 100, right? So it's a factor 10 here, right? So this term can be much smaller. It's much easier to drive down the probability of failure than to drive down the error with more observations. And that's kind of the general principle. So if you look in the notes and if you look much more in the Math for Data book, there's a longer chapter on how to formalize this idea of the concentration of measure as you get more data points, how this concentration squeezes, and how to think about these bounds. And in the homework, that's out and due in a week. There's a bonus question that I think is only worth 2 points, but it's about kind of playing with these formulas and deriving it. Okay, and it's the points are not, you know, it's 40 points to answer a maybe an easier question than